All right, so good morning, everyone. So incidentally, this is the last lecture for this week before we go on the mid-semester break. But it's also the last lecture on, the first half of the course on circuits and electricity, electric fields and magnetic fields. And then when we come back in week 7 after the break, we will look at a new topic on waves. But to wrap up the topic on AC circuits, right? We've been learning about the inductor being a circuit device that's the counterpart of resistors, but inductors only operate with alternating currents and voltages. So in this lecture, we will sort of combine all of the circuit elements that we have encountered in this course so far. We will look at how a resistor, an inductor, and a capacitor behave if they are connected in series together with an AC voltage source. Right? And just a quick revision of what we've learned. We learned that, if you have a coil and you rotate that in the magnetic field region because you are changing the number of magnetic field lines crossing this coil by virtue of changing the angle or the orientation of the coil in the magnetic field region, you of course have magnetic fields between these magnetic poles going from the North Pole to the South Pole. Then you are generating an induced voltage or induced EMF. And we learned that the induced EMF that's generated is sinusoidal in behavior as shown in this graph, right? And hence we call that an alternating voltage. So as we discuss AC circuits, we just refer to AC voltage and AC currents. Of course, AC means alternating current, so it's sort of redundant, but just for simplicity, we just use AC voltage for an alternating voltage source and AC current for an alternating current, right? So it's AC voltages and currents, they are defined by the sinusoidal graph, and mathematically, therefore, they are described by the sine function. Last time when we learned about the operation of a generator, we wrote the angle theta in terms of the angular velocity, recalling that the angular velocity is angular displacement over time, and hence, the angle theta can be written in terms of omega, which is the angular frequency. The angular frequency is related to the frequency of rotation, right? Frequency of rotation, meaning how many rotations will the coil have per second. And hence we can write the equation for the AC voltage as V max, the maximum voltage, right? Which is the peak or that maximum point there times a sine omega t function. And similarly for the current, we can write that as I max sine omega t, where I max is the maximum current. Right? But if we look at the sinusoidal graph, okay, here is the voltage versus time of an AC source. So you have a sinusoidally varying voltage magnitude. If we get the average of this, right, we can see that it's symmetric about 0 volts. So if we take the average of this sinusoidally varying voltage, then of course the average is 0. And hence, if we're talking about AC currents and AC voltages, it doesn't really make sense to use average values because the average is 0. So instead of using average, we use what we call RMS. RMS means root mean square. Value of the voltage. So how you apply RMS is you first take the square. If you take the square of the voltage and then take the mean or average, dividing the voltage by 2, and then you take the square roots of the voltage. And similarly, you can do the same thing for the current. Take the square of the current, then the mean or average, and then take the square root of the average. That will give you the RMS or root mean square value. And so these equations already did the maths for you, taking the square of this equation for the voltage, then the average, and taking a square root. And that's why you have here the square root of 2. That's coming from the square root of the average. Okay. All right, so you can calculate the RMS current by taking the maximum value divided by square root of 2. Similarly, for the voltage, the maximum value is, of course, right, the peak in your sinusoidal graph, right, and divide that by the square root of 2. Okay. The reason why we take RMS values is that if we consider RMS values, they have the same effect as DC values. It's as if, right, it's as if you are then considering a current or a voltage that's constant through time if you use RMS values. In fact, RMS values is what the multimeter measures. And hence, we can then, using RMS values, you can use the circuit equations that we've learned so far. For example, the power is equal to, this is coming from power is equal to current times voltage. You can apply this equation by using RMS current and RMS voltages. You will then get the average power. Right? So, right. So, yeah, you can read this, but in essence, it's what I said, right? In DC circuits, we use currents and voltages. In RC circuits, if we use, in AC circuits, if we use RMS currents and voltages, then it's as if we are looking at a DC circuit. And in fact, as I mentioned, multimeters measure RMS voltages and currents. So for example, when we say that the voltage coming from the mains outlet is 240 volts, what we actually mean is VRMS is 240 volts, right? AC current is coming out from the source, but when you measure it, you read 240 volts in your multimeter, and that's why we know the RMS voltage is 240 volts. If you want to get the maximum voltage that's coming out of the mains, then you still need to calculate that using this relationship between RMS and the maximum value. It's in fact 339 volts for a 240 volts RMS source. Right? Okay, so that's RMS values. Now let's look at how we'll now move towards analyzing AC circuits, right? But the thing to remember is that if you have an AC source, AC voltage or AC current source, you have this sinusoidally varying current and voltage. In this case, let's look at current, right? So that what that means is over time. So the y-axis here gives you current, and the x-axis gives you time. What that means is over time, the magnitude or the amplitude of the current changes. And so when we analyze, of course, it's described by this equation here. So when we analyze AC circuits, keep in mind that you have a sinusoidally varying current. And it's, I don't know about you, but it's a bit difficult to draw sinusoidal graphs accurately to visualize what's happening to the current and the voltage in the circuit. So instead of drawing the sinusoidal curves, we use what we call a phasor diagram to visualize what's happening to the current and the voltage as a function of time. A phasor diagram is essentially relating the sinusoidal graph to the motion around a circle, right? And hence I have these two figures here. On the right, you have the sinusoidal varying current, and that can be related to a vector or an arrow that rotates around the circle from 0 to 360 degrees. Okay, so that each point in your sinusoidal graph can be related to an angular position in your phasor diagram in the circular rotation here. So say, for example, this Imax value can be related to this arrow that is 90 degrees, that has rotated 90 degrees relative from the 0 degree origin. right? Okay, so we will be using phasor diagrams, but I will be showing the sinusoidal graphs as well in order to relate those two. So let's learn more about the phasor diagram. As I've already mentioned, the phasor diagram uses a phasor, and a phasor is actually a vector. So this blue arrow here, this is your phasor, which is the vector. It represents the current I in the circuit. The length of the vector should be equal to the maximum value of the current. And the direction, because a vector needs direction, so the direction of the vector, which is omega t, can also be written as the angle theta. Right? So the angle theta gives you the direction of the phasor vector. To represent the sinusoidal, like this sinusoidal graph here, to represent this in terms of the phasor, we say that the phasor rotates around the circle, just like this case, right? You have the sinusoidal graph that varies in amplitude with time that is equivalent to this arrow, this phasor that rotates around the circle. But the rotation goes in the anticlockwise direction at an angular speed of omega. So although I drew the current phasor to be in this orientation, through time, this phasor actually rotates, tracing out a circle as a function of time. Right? So the vector rotates anticlockwise at an angular speed of 2 pi times f, which is equal to the angular velocity. If we want to find the instantaneous current and voltage, instantaneous, again, is the specific current or voltage at a particular time t, right? Then the instantaneous current in this phasor diagram is this current here. Because at a particular instant of time when this phasor is oriented this way with an angle omega t, the current is this current. The maximum current is always fixed. Right? It's the maximum current that the voltage source can generate, so that maximum current is fixed. But this current, instantaneous current I, changes with time as the phasor rotates around the circle. Okay? And how do we find this instantaneous current? We find the instantaneous current as the y component of this phasor vector. Okay? In essence, it's this length here that gives us the instantaneous current. And of course, we can get the y component using trigonometry. Good. All right, so to emphasize what I've been saying about the phasor diagram being related to the sinusoidally varying current and of course voltage, we're just using current as an example here. So for example, you have this current, the y-axis is current, x-axis is time. Over time, the magnitude of the current changes. Say, for example, you want to find what is the current at this particular point in the sinusoidal graph, meaning what's the current at this particular time in your circuit. You can then project this sinusoidal graph to the circle, to the phasor diagram, and notice that at this point you're at an angle 30 degrees from the origin. That means the phasor vector would have rotated an angle of 30 degrees by the time your current reaches this point here. So when you calculate the instantaneous current is given by this equation I max sine omega t, right? Then your omega t will be equal to 30 degrees. I max, of course, is this maximum value. Whatever that maximum value is, sine 30 degrees will give you this current here. Okay. The instantaneous current will, of course, be this one, okay? Because your y-axis gives you the current. So the current at this particular instant of time will be this value here on the y-axis, which is equivalent to the length of this line here, which you can calculate as I max sine 30 degrees. Okay. If you project this line onto your phasor diagram, you will see that it's actually the y components of this I max vector that is equal to the instantaneous current. Does that sort of make sense? Okay, right? So say, for example, you want to draw a phasor for a current. The current is described as 0.02 amps. This is I max. Sine pi over 2, and the voltage is 3 volts sine pi. So let's draw the phasor for this. If we draw the current has a magnitude of 0.02 amps. The length of this vector should be equal to the maximum current. And then the angle is pi over 2. Omega t or theta is pi over 2, and hence, or 90 degrees, and hence your current is 90 degrees relative to the 0 degree reference. Okay. And then for your voltage has a length of 3 volts. Okay. So your phasor vector is longer than the current for the, voltage phasor is longer than the current. Because the maximum voltage has a greater magnitude compared to the maximum current. And then the angle is pi. Omega t is pi, or 180 degrees relative to the 0 degree reference. And hence you draw your voltage like this. Good. So this is a phasor diagram for this current and voltage equations. Right, the phasor, the current and voltage rotates anti-clockwise through time. So although these are drawn stationary, right, they will actually change, the orientation will change through time as the phasor rotates. And because we are moving in the anti-clockwise direction, that means that the voltage comes first before the current, right? Because we're moving this way. Hence, we say that the voltage leads the current. Okay, specifically, the voltage leads the current by 90 degrees, or pi over 2, because the angle between them is 90 degrees, or pi over 2. Good. Right, so if we can write the equation for the voltage, right, we can rewrite this as sine pi over 2 plus pi over 2. Pi over 2 plus pi over 2 is, of course, still equal to pi. But by writing it this way, you can see we can define an angle phi, which is equal to pi over 2, and phi is called the phase difference between the voltage. Right? If you compare the current equation, that's sine pi over 2, for the voltage equation, you have sine pi over 2, which is the same. But for the voltage equation, you have this extra plus phi, which means that there's a phase difference of phi equals pi over 2 between the voltage and the current values. And as you can see from the phasor diagram, the voltage leads the current by pi over 2, which is equal to the phase difference. Right? Is that making sense so far? Right? With phasor, we're just talking about phasor diagrams at this point. Right? So if we draw the sinusoidal graph for this phasor diagram, that means that the voltage leads the current by 90 degrees, right? So that's your current. Your voltage leads by 90 degrees, or pi over 2. It means that the voltage reaches maximum value first compared to the current. Say at time t equals 0, your voltage is maximum, your current is minimum. But after pi over 2 or after 90 degrees, the current will now reach its maximum value. Okay. So this is the phasor diagram. The voltage is leading the current by 90 degrees. This is the corresponding sinusoidal graph that is the same as this phasor diagram. You have the voltage that is leading the current by pi over 2. We know that the voltage is leading because at time t equals 0, the voltage is maximum first. And then after 90 degrees or pi over 2, the current reaches its maximum value. Right. So you can represent the current and voltages either using the sinusoidal graph, if you're comfortable drawing sinusoidal graphs, or a more simpler way of relating the current and the voltage is to draw this phasor diagram, because then you're just drawing vectors or arrows with the correct orientation and correct lengths. Good. And any questions about phasors, phasor diagrams, and voltages? Because then, right, if we're happy with the concept of phasors, we can then talk about the circuit elements in an AC circuit connected to an AC source. So let's look at each of the elements first, and then we will combine all of them. So first, resistor in an AC circuit. Essentially, you have a resistor connected to an AC voltage source, right? The resistor will just dissipate the current. It doesn't really change anything except the amplitude of the current. So if we describe the current and the voltage through a resistor connected to an AC, the voltage is in phase with the current. Right. Mathematically, they will take the same form. The phase difference is equal to 0. Or if you draw that in the sinusoidal graph, if the voltage is maximum, the current is also maximum. Right. Of course, once you connect the resistor to a source, current will flow through the resistor. So there's current through your resistor. And then there's also voltage across your resistor points. And so the current and the voltage, they are in phase. If you draw the phasor diagram, you can usually draw the current first, and the voltage is in phase with the current, right? They are in phase. They reach the maximum value at the same time, and they rotate around the circle at the same time. If you use the maximum values right here, maximum currents and maximum voltages, or the RMS currents and voltages, we can still use Ohm's law to analyze the circuit. So V RMS equals I RMS R, or you can use maximum values as well. Likewise, for the average power, the equation we used in circuits before can also be used. Just make sure you are using RMS values for the average power. Okay, and if you use this definition of Ohm's law, you can replace V with current, and you have this alternative form for the power. Right. So in other words, for resistors in AC circuits, you can analyze the circuits as we usually did with DC circuits. Just make sure you use maximum or RMS values. Now, for a capacitor in an AC circuit, okay, let's go back to what the capacitor does, right? We learned that the capacitor charges up if you connect it to a voltage source. And during the charging process, you, of course, start with a 0 charge and therefore a 0 voltage, but you start with a maximum current, right? Capacitor, and as your capacitor charges up, the voltage increases, but then the current decreases. In other words, in a capacitor, you have maximum current first and 0 voltage. Okay, so if we look at the capacitor connected to an AC circuit, it then makes sense that the current should lead the voltage. The current should lead the voltage because the current will reach its maximum value first before the voltage reaches its maximum value. And so you have this plus pi over 2 phase difference in the current. And if you represent that with sinusoidal graphs, okay, you have at time t equals 0, the current is maximum, but the voltage is 0, and over time the current decreases, but at the same time the voltage increases until the voltage reaches maximum value, and at that point the current is 0. Okay, so if we draw this sinusoidal graph using a phasor diagram, the current comes first, the current reaches maximum first. So you can draw the current first, and then your voltage comes before the current. Okay. Right, and the phase difference is pi over 2 or 90 degrees. So these two vectors should be perpendicular. Okay. Right, in this phasor diagram, we know that the current comes first because the vectors rotate around the circle in the anti-clockwise direction with angular velocity omega, right? So you're sort of going in this direction. So of course, this current comes first, and then the voltage comes later. And you have a 90-degree angle between the vectors. Right? Okay, now how do we analyze, how do we calculate? Of course, the currents and voltages at any time t can be solved by using this equation, just plugging in time values and omega values. But we can also use Ohm's law, right? Ohm's law, V is equal to IR, to find maximum currents and maximum voltages, or RMS currents and RMS voltages. So we can use Ohm's law, V is equal to IR, if we replace R with this quantity XC. And XC is what we call capacitive reactance. The capacitive reactance is like the counterpart of resistance in AC circuits. So it's as I say here, it's comparable to the resistance of a resistor. So by using the capacitive reactance, we can use V equals IR to calculate for the maximum currents or the RMS currents in your circuit. The capacitive reactance is defined by this equation here. You can calculate it knowing the capacitance of the capacitor and the angular frequency. Remembering that angular frequency is equal to 2 pi times the normal frequency. Normal frequency is how fast the coil is rotated to generate the voltage, the AC voltage in your circuit. Good. So let's look at this example, right? Your circuit consists of one capacitor. Capacitance is 1 microfarad, micro 10 to the minus 6. It's connected to a 120 volts AC power source. All right. We say only 120 volts AC power source, but it's understood that this is VRMS. As I mentioned, when we measure our voltage source with a multimeter, we're always measuring RMS values. And we want to determine the RMS currents if the power source has a frequency of 60 hertz and 600,000 hertz. So frequency in hertz, that is F. Okay, and we want to find the RMS current. We know the voltage, we know the currents. Oh, sorry, we know the voltage and we don't know the current. Yeah, as I think, yeah, I have the next slide here. As I mentioned, you can use Ohm's law. V is equal to IR. But instead of R, you can use R, because R refers to a resistor. In this case, you have a capacitor. Instead of R, use the capacitive reactance XC. XC is, of course, defined as 1 over omega C. Omega is equal to 2 pi F. And hence you have your XC is equal to 1 over 2 pi FC. Okay, right? Because if you know XC, VRMS is given, and therefore you can find IRMS. So the first step is to find XC, the capacitive reactance, right? 2.7 kilo ohms, given this frequency F, and the capacitance 1 microfarad. And once you know the capacitive reactance, you can then use this Ohm's law for AC circuits to find the RMS current. You have the VRMS that's given and the capacitive reactance you've calculated. Right? Changing the frequency doesn't change the calculation steps, right? It only changes the value of the frequency F there. And then, of course, the current changes accordingly. Right? Good. Any questions so far for the resistor or the capacitor in an AC circuit? Okay, now for the inductor in an AC circuit, how does the current and the voltage behave? First, let's go back to what the inductor does, right? Yesterday, we learned that the inductor sort of acts like a resistance that impedes AC currents, meaning if there's a change in the amplitude in current, the inductor kicks in to try and oppose this change. So going from a zero current to some current value, the inductor will try to keep the current zero, and then let the current increase gradually over time using via the exponential equation we learned yesterday. So if you think about that, the current doesn't increase immediately if you have an inductor, but there is already voltage in your circuit, right? So therefore, in an inductor, the voltage across the inductor will come first before the current, right? Okay, because the inductor opposes any change in the current cannot increase instantaneously. I mean, the current cannot increase right away, but there is already voltage across the inductor because of the changing current in your AC circuit. Hence, the voltage will lead the current. The voltage will reach maximum value before the current. So if you look at the sinusoidal graph, you have the voltage having a maximum value first at time t equals 0 when the switch is closed or when the inductor is connected to the AC source, right? The current momentarily will still be 0 as the inductor opposes the current flow, but there is already voltage across your inductor. Over time, the current increases exponentially until it reaches its maximum value, right? And at the same time, as the current increasing, the voltage decreases. When the current is maximum, the voltage is 0, right? And so if you draw your phasor diagram, the voltage comes first, right? So here your voltage comes before your current, and there's a phase difference of pi over 2 or 90 degrees between the voltage and the current. Of course, your phasors still rotate in the anti-clockwise direction, and hence this orientation tells us that the voltage comes first before the current if you have an inductor. Okay, similarly, you can apply Ohm's law, B is equal to IR, if the resistance R is replaced by XL, which we call inductive reactance. Remembering that when you use V equals I XL, you should use the maximum currents and maximum voltages, or RMS currents and RMS voltages. So in other words, Ohm's law will allow you to calculate maximum current or RMS current. But if you want to find the specific currents at any instant of time, then use these equations to find the current at some time t, or find the voltage at some time t. Okay, so that's the difference between these equations, the sinusoidal equations, and the V equals IR equations there. Okay. The capacity, inductive reactance XL is defined as omega times L. L is the inductance of the inductor. All right, so let's look at this example. You have, let's just look, you have a coil that has a resistance R equals 1 ohm and inductance 0.3 Henry. It's connected to a 120 volts AC source at 60 hertz. We want to find the inductive reactance of the coil and the current in the coil. So inductive reactance, this is just from definition. XL is equal to omega L. Omega is also equal to 2 pi F. F is the frequency of the AC source, 60 hertz. Yeah, so you have everything. You have XL is 113 ohms. Right, and once you know the inductive reactance XL, you can always use the Ohm's law counterpart for the AC circuits. V is equal to IXL to find the RMS currents in the coil. Right. We know we can find RMS current because, again, as I mentioned, when we say the voltage source is 120 volts AC, it's implied that this is VRMS because it's what we can measure using a multimeter. Yeah. If we mean maximum voltage, we will specify specifically that the maximum voltage is such and such volts, and therefore it will be maximum current that you will be calculating using that maximum voltage. But in this case, what's given is the RMS voltage, and hence what we can calculate is the RMS current. But of course, there's nothing stopping you from calculating the maximum current, because we know that the maximum and RMS are related to each other via this equation that we saw. So once you know the RMS current, you can always calculate for the maximum current by multiplying the square root of 2. Good. Right, so this table just summarizes everything we learned for resistor, inductor, and capacitor. I usually use this mnemonic Eli the Iceman to sort of remember that in an inductor L, the voltage comes first before the current. In a capacitor C, the current comes before the voltage. Okay. And yeah, because now we will combine all these R, L, and C in a series circuit connected to an AC source, right? We know that if they're all connected in series, the currents flowing through them is the same, right? And the voltages add up. Okay? So how do we analyze the circuit for the currents and the voltage? First, we draw a phasor diagram, and then we try and yeah, so it's still the same strategy we learned before with resistors in series and parallel, right? When we learned about resistors in series and parallel, we tried to simplify the circuit so that we have just one resistor and a voltage source. we will use the same strategy to analyze the circuit, trying to reduce this into a single voltage and a single current, and then we can use V is equal to IR to calculate for the voltage and the currents, right? So that's the strategy we will use. The first step is to draw a phasor diagram so that we can visualize what's happening to the currents and the voltages in the circuits. So let's draw the phasor diagram. Okay, you have an inductor, a capacitor, and a resistor in your circuit. So if I use the mnemonic Eli the Iceman, you can always draw the current first. Okay? You can always draw the phasor for the current first because you know that the current is the same for all the circuit elements. So once you've drawn the current, you know that the resistor voltage is always in phase with the current through the resistor. So you can draw the voltage of the resistor that's in phase with the current. Okay, and for the inductor, the voltage comes before the current, right? So that means that the voltage in the inductor comes before the current, and they have a phase difference of 90 degrees as we saw earlier. And for the capacitor, the current comes first before the voltage. So using the current in your circuit, that's your reference phasor. The voltage of the capacitor comes after the current phasor in your circuit. So you have this phasor diagram for the currents and the voltages across each of the elements. Okay. Right, the voltages, these are vectors, so you can look at them as vectors, these arrows. Right, you have the capacitor voltage pointing downwards and the inductor voltage pointing upwards. And we already know that two vectors in opposite directions can be subtracted. So we can subtract these two vectors to simplify our phasor diagram. You then have VL minus VC, right? That's subtracting these two voltages there. And then the voltage for the resistor is still the same there. You have essentially a horizontal voltage and a vertical voltage. The sum of that voltage is therefore the hypotenuse of the right angled triangle. Hence, we are able to find the maximum voltage, which is also the voltage provided by the AC source. Okay? So the maximum voltage is the hypotenuse of this right angled triangle, which we can calculate as the vector VR plus the vector VL minus VC. Okay. Or in terms of magnitude, we use Pythagoras theorem. The magnitude of this diagonal vector is the square root of the horizontal vector squared, which is VR squared, plus the vertical vector squared. The vertical vector is VL minus VC squared, right? So that gives us the magnitude of this diagonal vector Vmax from the source. Okay. Expanding definitions for voltages using Ohm's law. Okay. V is equal to IR. Don't forget there's a square still there. VL is equal to IXL and VC is equal to IXC. Okay. Again, there's a square there. They are all connected in series, so the currents are all the same. You can take out the currents from, you have current in this term, current in this term, so you can factor out the currents. You have current squared, take the square root of that, and hence you have the current being taken out of the square root. Okay. Right. This equation now sort of looks familiar. We compare that to V is equal to IR, right? Ohm's law. It looks very similar. And if we, it looks very similar to V is equal to IR if we write that as Vmax is equal to Imax times Z, where Z is this whole square root thing, square root of R squared plus XL minus XC squared. Okay. So Z, right, can be thought as the effective or equivalent resistance in an AC circuit. What we did is we had this RL and C in series. We sort of got their effective resistance in terms of, but by doing some vector algebra, and their effective resistance is given by this equation by Z. Z is called the impedance of the circuit. Impedance, in other words, is sort of like the effective or equivalent resistance in your series RLC circuit. Right, and we know that the concept of resistance and therefore impedance is to impede the flow of current, to control how much current in your circuit. So this is some sort of a resistance. Hence, if XL is equal to XC, you have this thing being equal to 0. XL minus XC will be equal to 0 if XL is equal to XC. And in that case, the impedance is just equal to the resistance R. In other words, the impedance is minimum and the current will be maximum. All right. And in that condition, when the resistance or impedance is minimum, where XL is equal to XC, XL is equal to omega L, XC is equal to 1 over omega C. We can combine omegas together. Hence, you have omega squared is equal to 1 over LC, right? And that allows us to find the frequency for which the current will be maximum in your circuit, in the circuit. And that frequency is what we call the resonance frequency. All right. Okay, so key takeaways. We did a lot of derivation, but the key takeaways, if you have a series RLC and RLC circuit, you can use this equation here to find the maximum current given the maximum voltage. Of course, you have, this is the effective resistance. Now, in terms of finding the power, right? In terms of finding the power, we need to first find this Vmax, right? To find this Vmax, we can relate that to this angle phi, right? This was the vector diagram we had simplifying the phasors for the RLC components in our series circuit, right? To find this phase phi, we can use trigonometry because you're forming this right angled triangle, right? If you take the cosine of this angle phi, cosine will be equal to the adjacent side, VR max, divided by the hypotenuse, which is V max. In other words, V is equal to IR and V max is equal to IZ. In other words, cosine phi is equal to R over Z, and we call this the power factor in the circuit. We sort of need the power factor to find the power in our series RLC circuit. Okay, so if you find the power, power is defined as power is defined as average power is IRMS, VRMS, right? But using, of course, the definition for VRMS is equal to IRMS R, we can also write the average power in terms of the current only. Okay. So the resistance R it's not just the resistance of the resistor, but it's sort of this R coming from the power factor. So from the equation, R is equal to the impedance times cosine phi. Hence, we can rewrite the power as I squared times the impedance cosine phi. Right. So in your series RLC circuit, the power is not just simply current times voltage. You need to consider this cosine phi factor in addition, which is called the power factor, because this cosine phi comes into the angle between the vectors. Okay. Right, and this is just a quick note. What happens to phi if you only have a resistor? Phi is equal to 0, and you reduce to the same power equals IV. Right. Good. It's quite a big lecture about AC circuits, and it's just talking about the concept. So the workshop this afternoon is really the place where we can practice analyzing AC circuits. But in this course, you will only encounter series RLC circuits. Parallel RLC circuits are more complicated and beyond the scope of this course. So if there are any questions, I'll take it outside because the next class is here. But otherwise, I'll see you in the workshop this afternoon. Or otherwise, if I don't, I wish you a good break and see you after the break.